Greeting, guys and girls. Hope everybody had a good weekend. What I wanted to do with you guys today was quickly recap what I sent your way in the PowerPoint on Friday, which was all about phase changes. Talk a little bit about those. And then more importantly, start to get into the way that heat factors into these phase changes, which links all of the different things we've been talking about in the last weeks with solids and liquids more recently, and then gases prior to Easter break and before. So when we're talking about phase changes, try to quickly show you guys the most important things about them. What are our phase changes and how can heat be affected? So part of understanding what happens with your phase changes is understanding what the particles look like, which I think based on everything I'm getting from you guys, you have a good idea that the solids are very tightly packed, that my liquids are still closely packed, but a little bit more space, and that my gases are far apart, moving around the whole time. So if we start to get into changing this phase, we are not altering who the particles are. That would be a chemical reaction. We're simply altering the distance between those particles, either making them closer or making them further apart. We're also altering the speed that they move at. So it's a change from one state of matter to another. They're physical changes because it only affects the appearance, not the chemical makeup. Like I said, heat is a big factor in this. If we want certain things to happen, we give it heat. Other phase changes require the loss of heat, right? And one thing you want to understand is in chem, there's no such thing as cold. There's simply heat entering and heat exiting. You would perceive heat exiting as the feeling of coldness, but it's simply thought of as heat moving one way or the other. So during a phase change, heat is either absorbed or released. Energy is released and molecules slow down. And when they slow down, they can move closer together. And what you're going to find is that they have the ability to form intermolecular forces. On the other hand, if we heat up substances, they tend to want to speed up. And because they have this additional energy, they're able to overcome the hydrogen bonds and dipole-dipole forces and London dispersion forces, those IFs that hold them together, and they're able to break apart, and that allows them to expand in certain cases. So there are 6 fundamental ways that phase changes occur, but they live in pairs, right? Because they can go in opposite directions. Now I have slides for each of them after, but this does a good job of showing you all of them. Right? I have a solid linked with a liquid. If the solid becomes a liquid, we call it melting. If the liquid becomes a solid, we call it freezing. So think of that like a two-way street. Particles are packed very tightly together in the solid. In the liquid, they're a little bit further apart, and we can make them be one or the other by manipulating the heat. Liquid to gas, same idea. You've got particles pretty close. Gas has particles far apart. We can take the liquid and turn it into a gas through vaporization, which includes evaporation and boiling, or we can make them come closer together by condensing them. The two that you're probably the least familiar with would be examples of solids going directly to gases or gases going directly to solids. Like these are called sublimation and deposition. All right, solid to gas is sublimation. Gas to solid is called deposition. So let's take a look at those individually and talk about how they happen. And if I want to melt something, we're talking about changing a solid to a liquid, and heat is involved with that. Heat very often is translated into kinetic energy. So if I want a solid to become a liquid, it needs to absorb energy. We need to absorb energy into our solid crystal, allowing those particles to vibrate harder and harder and shake more and more and more till finally there is enough energy present to overcome the IFs that hold it together, and the liquid will form. On the other hand, if we were to reverse that, we want a liquid to become a solid, we need to slow molecules down so intermolecular forces can form. So in this setup, if a liquid wants to become a solid, we need kinetic energy to leave. We need to slow down the motion. We need heat to exit. So the kinetic energy, right, is given off in this setup, and a byproduct of that is that the particles can't keep their same speed, so IFs take over and lock the particles in place. That would be freezing. The other two follow the same pattern. It's just the distance between the particles that vary. If I want to vaporize something, I'm talking about a liquid going to a gas. The particles are closer in a liquid. If I want them to be further apart, I need to absorb energy because the gas moves much more than the liquid does. So we give it that heat, the particles speed up, and they can separate. The reverse of that, if something wants to condense, we're talking about a gas going to a liquid. If we want a fast-moving gas to be able to form liquid droplets, we need to slow those gas particles down so IFs can take over and form that drop. Anytime we have heat exiting, we call that exothermic. Whenever heat is entering, when we're heating something up, that is endothermic. So those terms will get used interchangeably. Heat leaving, exothermic. Heat entering, endothermic. The last two, the ones that you're probably not as familiar with, is sublimation. And tomorrow, I have a pretty cool demo set up for you guys that I can play a video for you of. I would usually do it in class, but I found a good comparison that I hope you guys think is cool. Sublimation is often done with dry ice, solid carbon dioxide. It gains energy and it immediately goes to a gas. You do not see the liquid form, which you'll find out later has to do with the pressure that would require. All right, so we're talking about a solid going to a gas, and again, the gas moves much more than the solid does, so the solid must absorb endothermically energy. And the reverse, which is more rare, deposition. Right? That is a gas turning immediately to a solid. One of the rarer ones that you might know is hail, right? Gases cool super quickly in a cloud, and instead of raindrops falling, you get those very tiny salt-looking spheres that can dent your car. And that would be a good example of deposition. So we have a gas that needs to slow down rapidly to form solid. It must lose a lot of energy quickly, so this would be an exothermic reaction. All right, and then those last two slides just recount all of those things and what's going on. So what I wanted to do was I wanted to dive a little bit deeper into the whole idea of heat and why this happens. All right, so to do that, I want to be able to draw some particles for you. So if you take a look, all right, at our screen right here, I'm going to focus in on melting. And if we're going to do this, I want to draw what these things look like. Now, let's just say, for argument's sake, that we are working with water. If I have solid water, which you guys would simply call ice, we know that the particles are very tightly packed together. And there isn't very much space between them. And the reason they're so tightly packed is because the intermolecular forces that are holding that solid together. So right here, we're talking about regular old-fashioned ice, which is H2O in the solid form. So if I wanted to become a liquid, my liquid, they're still pretty close, but there's much more motion between the particles in my liquid. So if I want this to become this, I need to overcome some of these intermolecular forces. And this is why substances melt at different temperatures, depending on who these particles are. These intermolecular forces will vary. If this is a particularly strong connection, like a metallic bond, the intermolecular forces are very, very, very strong. It takes an immense amount of kinetic energy, which is most often provided by heat, to break those intermolecular forces, allowing those particles to be able to move around each other. So the stronger the connection here, the more heat required to overcome those forces. If this is a weaker substance, like a London dispersion force, which is the weakest of them, it might not require very much heat at all to do that. So the take-home message that I want you to understand from this, right, is what I'll type here for you. All right, kinetic energy is needed because you have to overcome the intermolecular forces holding the solid together. So the reason that we need heat is because those forces of attraction have to be overcome if we are going to separate those particles. And that is why 3 of our phase changes are endothermic. I could make this equation manipulate very easily into vaporization by simply getting rid of the word solid and writing liquid, and getting rid of the word liquid and writing gas. Right now, when I do that, things change. Right? The reason why it's not the same exact temperature that a solid melts and a liquid boils has to do what's happening. Here's your solid to liquid. If I bring you up a new screen and I'm trying to go from the liquid to the gas, my pictures vary. My liquid is relatively close, and there's intermolecular forces holding it. But not only does my gas have to separate each and every one of those particles from each other, if a gas wants to behave like a gas and expand, it also has to overcome atmospheric pressure that's pushing down on the liquid. Melting, we don't care about that because the liquid particles aren't trying to leave the container. So it takes a smaller value to make a substance simply overcome its IFs than it does to make the substance overcome every single IF that connects them all and overcome that force coming down from above that the gas would have to overcome for this particle to escape. So it takes more energy. So we still list the equation as having plus kinetic energy over here. Right? But it's more kinetic energy, which is why water melts at 0 degrees Celsius or 32 Fahrenheit but it boils at 100 degrees Celsius and 212 Fahrenheit. Right? So that's what's going on with your endothermic processes. If we looked at an exothermic process, right, we reverse one of these guys. The process is still linked, but it's different. Let's say we're looking at a gas wanting to become a liquid. You guys would call that condensing. So if we look at the particles, we know our gas looks like this. They're spread out and they're moving very quickly. If we want to make them look like this, like the liquid, what has to happen is we need to slow these gas particles down. We have to slow them down long enough that we have the chance for intermolecular forces to form in between these particles. So if we want a gas to become a liquid, we need to form. Intermolecular forces. Before, we wanted to overcome intermolecular forces. And if you want to overcome forces, you need heat to break those forces. But we don't want that. We want the gas to become a liquid. So we need to slow these guys down so that when they bump into each other, there's enough time for new IFs to form, which is why kinetic energy has to be lost. We must lose heat from this process to make that occur. So that's the whole idea behind all of your exothermics. We're slowing particles down to allow new IFs to form, locking the particles in place, or in this case, taking things that were very far apart and forming new IFs to get them much closer together. So that's what's going on with the heat aspect of phase changes, whether it be melting, boiling, freezing, condensing, sublimation, deposition. So in class, what I always like to do are throw out two scenarios. The first one is this one here. All right. And I always have people just take like 3 or 4 minutes, all right, to write down why they think this occurs. So in Florida, people that grow oranges spray their crop with water if it's supposed to get below freezing that night. Every once in a while, you get a late cold snap. All right. And if it gets below freezing, that's bad for the orange, because if the juices inside the orange solidify, we know they expand, it ruptures the orange, it's ruining the crop. So what they do is they spray the oranges with water, right? Specifically if they know it's going to freeze, and it saves the crop. So what I want you to do is I want you to think what phase change is going to occur when this happens at this temperature, when it gets below freezing, and then why does this protect the orange? How is it that we keep heat in the orange by spraying it with water? That's scenario number 1. Scenario number 2 is the one you see here. In the summer, you swim around in a pool that's 75, 80 degrees. You get out on a hot summer day and the air outside you is north of 90 degrees a lot of times. But a lot of people will begin to shiver, and a lot of people will get goosebumps when this happens. Those are both signs that are saying you're cold, that your body is cold. But why would my body be cold if I'm going from a colder situation to a warmer situation? I should feel warmth instead of cold, right? So again, I want you to tell me, what phase change do you think is in effect, and how do you think this creates the outcome? All right, so the homework for tonight, all right, that I want you guys to send me are your explanations. It's as simple as a phase change and why it protects the oranges, and a phase change and why you shiver under these circumstances. And that's what you think, right? Tomorrow, right? I'll have some dry ice videos for you. All right. And then Wednesday, we'll kick off class with the answers to these questions. All right. And I'm going to get into a bit of the math behind the heat of these phase changes. I hope everybody's doing well. This will all be coming to you in a parent square, but the questions are in the video, and I don't want to attach too many things. So make sure you guys watch the video to the end, because the questions are there. Hope everybody is doing good. I look forward to hearing from everybody.